Perfect, great. So hi everyone. Welcome to the last week of the CPBF summer school. You've made it to the end, so congratulations. My name is David, and I'm a professor at the Initiative for the Theoretical Sciences at the CUNY Graduate Center and part of the CPBF, which is joint between Princeton and CUNY. And I'll be telling you today about a topic that's a bit different in flavor than what you've heard about for most of the school, and that's focusing on the statistical physics of machine learning. And get this to work, great. And I want to emphasize that my aim here is not to give you a general introduction to machine learning, nor is it to give you a set of tools that you can use to apply to the data that your lab or your future lab collect, but rather I want to make the case for you that studying artificial learning systems in and of themselves are interesting, and that with a background in statistical physics and or neuroscience, you might have a tool set that gives you a unique and useful perspective. So there are many areas of machine learning that do have connections to statistical physics that I won't be covering. I won't be covering something called unsupervised learning or self-supervised learning or generative modeling, if you know what those words mean. I won't be covering reinforcement learning, and I won't be covering sequence models or natural language processing. You might have seen, if you're on Twitter, you might have seen people quoting GPT-3 recently, so I won't be covering anything like that. I'll be covering the sort of core basics of supervised learning that Wave and others introduced earlier today. So just a brief outline of what I'll be telling you. In the first half of the lecture, I'll be revisiting and reintroducing what are the core concepts in machine learning. We'll talk about something called the bias-variance decomposition, which is pretty fundamental to understanding what's going on when you do machine learning. I'll give you another brief introduction to neural networks, similar to what Tankut did a bit earlier, and then I'll give you some modern mysteries that might make you question what you think you know or what I just told you in the previous minutes about how modern models work. And I also want to emphasize that a lot of the first part of this lecture is taken from a review article that my colleagues and I wrote last year on an introduction to machine learning for physicists. It's fairly long, but we tried to be as concise as possible while introducing core concepts. It also comes with around 20 Jupyter notebooks that allow you to reproduce a lot of the figures and experiments that are in the paper, and I encourage you to take a look at those and play around with them. And in the second half, I'll tell you about something that's more research than it is pedagogic, and this will be some work using a sort of physics perspective to think about what stochastic gradient descent is doing in big neural networks. Okay, great. So let's get started. Let's first talk about an example of a learning problem. So what I've done here, and I don't want to have any equations, is in the top left figure here, I've taken a line and I've sampled 10 points from the line, and then I've fit to those 10 points either a line, a third order polynomial, or a 10th order polynomial. And what you see is that, of course, all three of these do a perfect job of fitting those training data. If I then sample new points from that line that originally generated the data, and I sample some points in the domain 0 to 1 where I initially had training data, but then I even go beyond the domain where I originally sampled points, you see that all three of these models, and you can't see the colors because they're all on top of each other, are doing a perfect job of not only fitting the data that I asked it to, but actually predicting on new data that that I'm testing on. If I do the same experiment where instead of generating the 10 points from a line, I generate them from a 10th order polynomial now, you find that the line in red does the best it can to fit the data, but it can't do great. The cubic does a bit better, and the 10th order polynomial goes through the points perfectly. And now if you ask on new data samples, how do you perform? The 10th order polynomial does the best because that was the model class that that generated the data. And so when I was first learning about statistics, when I came from theoretical physics and I had never worked with data, I thought I had in my mind that this is what learning is like. It's curve fitting of points. And the problem is that this is almost never the situation that you're in the real world. The real world looks more like this. If I can get there, like this, where I've essentially done the same experiment that that I had before, but now I've added noise. So here, sigma equals 1 indicates that I'm going to add some noise to the data. So in the top left plot here, I've generated data from a line, but then I've added that noise to it. And then I've tried to fit to those points a line, a third order polynomial, 10th order polynomial. And you see that the line and the cubic sort of try to get the general trend, but they can't do much more than that. The 10th order polynomial is a bit more ambitious and tries to fit some of the wiggles of all of these data points, but those wiggles are really just fitting randomness because of this noise that we've added. So when you go to look at test data, you actually perform worse with that 10th order polynomial, and you do better with the line and the cubic. And you say, well, that makes sense because the actual true model that generated the data without the noise was a line, so I'm not that surprised. But if you do that same experiment and now the true model that generated the data is a 10th order polynomial, and then we add noise again, there isn't much of a trend, so the line is pretty flat. The cubic again tries to fit a little bit of the ups and downs, and the 10th order fits a lot of the wiggles. But now when you look at testing data, even though the 10th order polynomial fit the wiggles of the training data the best, it still predicts quite poorly. And in this case, the third order polynomial is doing the best, especially outside the domain where we had sampled data. And so even in this case where we might have known that the true model that generated the data was this 10th order polynomial, we actually do a better job of making predictions by using a simpler model, by using the third order model. And at first that's somewhat surprising. You should think that, oh, if I know what the true model that generated the data is, I should just use that. And you might say, well, maybe this is because I didn't sample enough points. I only sampled 100 points. So maybe if I sample more points, then I'll get that 10th order polynomial back. And so here I've sampled 10,000 points from that 10th order polynomial and fitted it back. And even then, still, if you ask about new samples that you didn't train on, especially outside of the domain where you generated, you ask it to extrapolate, the 10th order polynomial eventually turns around and predicts quite poorly, while the third order is making more reasonable predictions. So even with lots and lots of samples, surprisingly large number of samples, the more complex model is not performing as well as you might expect. So how can we make sense of this? There are a couple of different lessons that I want to give you, some intuitions that I think are useful when thinking about learning from data in general. And the first is to think about how my performance changes as I have more data points that I'm fitting. Let me also emphasize that I have the Q&A window open, and you should feel free to type in questions anytime, and I'll try to monitor it as much as I can. I may not get to everyone's questions, but I'll do my best. So if we think about how your performance changes as we get more training data, there are two different kinds of performance we're interested in. One is the performance on the data that we use that we fit the model to. That is the training data. So there's an error, what's called in sample. So E sub in stands for in sample, or the training error, and that actually goes up as you get more data. That might be surprising, but the reason is that if you only have one data point, you can probably fit it perfectly. If you have two data points, you can fit it perfectly probably. And eventually, as you get more and more data, the true complexity of the data generating process is sort of revealed to you, and it might be outside of the scope of what you can possibly fit. And so as you end up with infinite data, there might be structure that you can't capture with your model, so your error will asymptote to something that is non-zero. And that asymptote is called the bias. And the idea is that your model is biased, and that it's unable to capture certain structure, and so you have this fundamental amount of error that you can't overcome. However, when you ask about the error on the new test data that you didn't train on, that's called out of sample, that is typically higher than the in sample error, and that is you expect to be monotonically decreasing. As you get more data, you'll learn more, and you'll be able to make better predictions. And the excess amount of error beyond this asymptote is called the variance. And why it's called the variance, we'll come back to in a little bit. The third concept that's worth mentioning is the difference between how well you perform on the training data and how well you perform on held out data. And that difference is called the generalization gap. And we would like to have that gap be as small as possible, so that that we perform as well as possible when we make predictions. But ultimately, all we care about is how big this E out is, irrespective in some sense of how big the gap is. So that was so this plot is thinking about how your performance varies as you change the amount of data that you have. Now, if we instead hold the amount of data fixed, but we vary how complex our model is. So think of complexity as sort of the order of the polynomial that we are trying to fit. Then as your model gets more complex, you expect the bias to go down, right? We're able to fit more wiggles. We're able to see more structure. So we expect the bias to go down. However, it's often the case that the variance component goes up, is actually increasing. And since we said that the out of sample error is a sum of a variance and a bias term, one's going down, one's going up, often you expect there to be an optimum trading off having minimal bias while also having minimal variance with somewhere with intermediate model complexity. And so another way to see this is to think schematically in model space. So imagine that the data came from a true model indicated by this this red circle, and then we fit two different kinds of models to that. One will be a very flexible model, so it has low bias. It can do a lot of things, and in particular, it can do what the true model does. So think of this like the 10th order polynomial. But every time you get a data set of a certain size, you'll get a different model that you fit. The parameters that you fit will be different. So you'll get all these different x's. So although the true model is in the sort of space of what the the model we're fitting is able to do from the data samples that we have. We don't always get that model, we get something else, and there might be a large variance around the true model. On the other hand, if we fit a less complex model, so think of this like the third order polynomial, then every time we get different data sets sampled from the true model, it kind of reliably gives the same thing, and that same thing is never aligned with the true model. There's always some distance away that you are, but you're getting something reliable and it's not too far away. And oftentimes this can be a better situation than this high variance case where you really don't know what you're going to get any realization of the data set. So this notion of having variance and bias sort of contributing to your performance on how.data isn't just a cartoon. You can actually quantify it and define things mathematically. I'm not going to go through a full derivation of this. I should say that the ITS, the Initiative for the Theoretical Sciences, also hosted a summer school this summer, and this lecture is essentially a 1 hour distillation of 4 hours of lectures that I gave there. So if you want to see more details such as this, which I'll end up skipping over, that's on YouTube. So if you search for Initiative for the Theoretical Sciences, you can find the YouTube channel and look at those lectures. But very briefly, the idea is, let's say that we have some data set. So we have some X inputs and we make predictions Y. So in the case of the experiments that I had a couple slides back, Y is just a continuous variable that we're trying to predict. And let's imagine that this data set was generated from some noisy process. There's some function F that takes the input X, maybe highly nonlinear. And then there's some added noise, and that produces the outputs Y. What we would like to do is to make a model of this data, and I'll call that F of X and theta. And if I were smart, I would have used a different symbol here than here, but this is the notation that we used in our review, so I'm sticking with it. But this is a process in the world that you have no direct access to. This is your model that you do have access to and has parameters. So you can distinguish them by when there are parameters associated. That's your model. And what you would like to do is find the values of the parameters that give you the best performance. So how do you measure performance? Well, with a task like this, your performance could reasonably be measured with the squared error, the mean squared deviation between what actually the world produced and what your model predicted. And you find the parameters theta by minimizing them so they are the argmin. And what I want to emphasize is putting a subscript D on the parameters that you find is that the fitted parameters depend on your data set. So if you imagine a multiverse where you get different realizations of data sets from this process, every time you fit from one of those data sets, you'll get different values for these parameters. And let's say you do that, then the way that you would measure your performance is to ask about the same squared error, not on the data that you trained on, but on new samples from this process that you didn't train on. And this is what I'll skip over, but you can actually do some simple analytic calculations that study the average performance on new data when you predict with those parameters that you fitted. And what you end up finding is that the total error can be decomposed into really 3 terms. So I added some noise. So there's some fundamental noise that you can't get surpassed. And then there's a bias term and a variance term. And these have nice interpretations. The bias is defined by this equation. In words, what it means is you want to look at the difference between what the model, what the true world model, the world process produces on samples, and what your average model produces. So this is now averaging the predictions of your model over realizations of the data set. So any one of them depends on the data set because of the parameters, and then we average that. So if there's a deviation here, that's not due to sort of a statistical artifact of having limited numbers of samples. It's really that your functional form of your model isn't able to capture all of the nuances of the true process. So that's why this is called bias. On the other hand, the variance term makes no reference to the world, to the process that generated the data. It's only about the model. So here, it's looking at the squared deviation between what the model predicts with a particular realization of the data set and the average predictions made when you average over data sets. So if you always get kind of the same model every time, it makes the same predictions, then the variance will be very small. But if the model is learning very different things on different data sets, then you will have a large variance. Let's see, let me check some questions. So yeah, so there can be different settings of model parameters that make very similar predictions. And so you can see here that variance is defined not in terms of how much the parameters themselves vary realization to realization of data sets, but rather how the predictions of the model vary. Put that down. And so if someone, I'll add a link to the YouTube later, but if someone can do that for me, that'd be great. So more complexity means lower bias, in the sense that if I think about complexity as the order of the polynomial that I'm fitting in that toy example, then as I have a higher and higher order polynomial, then I'm able to fit a more diverse set of functions. So I should be able to reproduce the true world model more closely if my model is more flexible. No, I don't think the in sample and out of sample are necessarily symmetrical around the bias. That's just a artifact of our cartoon. Thank you. Thanks for linking to the lectures. Let's see. Okay, great. So this is the general framework that I think is a good starting point for thinking about how learning works in general. We'll come back to this later because there are ways in which neural networks sort of violate this picture. In some sense, this bias-variance decomposition is just true, but some of the other intuitions that I told you we'll have to revisit in a couple of slides. So now I want to move on to neural networks specifically, and what are neural networks and why would you use them? So neural networks at this point are quite a large field. So defining them simply is not that easy. But roughly speaking, you should think of neural networks as models that learn multiple levels of features instead of hand designing them. What does that mean, and why would you like to do that? Well, if you're an expert and you know a lot about your data, hand designing your features could be a good idea because you can impart a lot of knowledge. But it's a lot of work, and you might not know. Maybe nobody's an expert in your data. So learning features is in some ways better than hand designing them. And so by features, I mean something like, let's say you want to quantify behavior and you want to track bees in a movie. And you might say, I know what bees look like. I know that they have stripes. I know what their shape is. So I'm going to make features that are sort of hand tuned to bees. And that can be useful, but maybe there are properties of bees that are more useful for tracking that you don't know about. So learning those features could be useful. So why multiple levels of features? In some sense, there are open questions related to this, but you can think of this as a sort of inductive bias, using the word a little bit differently than before, but similar, of having multiple layers that is useful for many interesting data sets. The idea being that a lot of data that is natural and that you might want to work with has structure on many different scales. So you would like a model that respects that and is able to extract that structure at different scales. So for example, in this diagram here, you might, and after training a neural network, you might find in the early stages of the model, the features that it learns look like oriented gabors. If you go to a little bit later in the model, you'll find, so this is imagining a model that's trained on a data set of faces. Later on, you might find that that there are units in the network that respond to parts of faces, like eyes and noses and ears. And when you get to the latter stages of the model, there are entire faces that are sort of being represented. There are features at different scales. Another reason for why to use neural networks is that they're actually fairly easy to implement now with frameworks like PyTorch and TensorFlow, and they're also easy to customize. Okay, that's why you might want to use a neural network at a very high level, but what are neural networks? So a lot of this will be redundant with what Tankut told you, and you've probably seen this before as well. But in the simplest form, a neural network is a feed-forward graph of nodes that perform a simple operation. And the operation that is typically performed is you have some input that's coming into the node, and that input is multiplied by a parameter vector w, and we're going to learn those parameters. So let's imagine that we have these, or we just initialize them randomly, and then we might have another parameter for offsetting. So we have an affine transformation, and then we take the output of that transformation and we send it through a nonlinearity. And so historically, that nonlinearity, which goes by the name sigma, was something like a tanh or a sigmoid. But in the past 8 years or so, people have found that a model called a rectified linear function works a lot better, which sort of zeroes out anything below a threshold, and then is just the line y equals x above the threshold. So this is what an individual unit is doing, and then what you do is you take these units and you wire them up, as I mentioned, into a feed-forward graph. And the first layer of units, the input is actually the data itself. These could be pixels of an image, they could be activities of neurons, they could be anything. So the first layer has a sort of different kind of input in that it's actually data, but then after that, every layer subsequently receives inputs that are the outputs of the previous layer. Eventually, you get to an output layer where all the information is combined, and the model makes a prediction. I mentioned squared error before, but often these neural networks are used to make discrete predictions about classes, meaning like, is there a cat in the image or is there a dog in the image? And so a cost function that is used for for that kind of task, instead of squared error, is called the cross entropy. It's written down here. I don't want to go into too much detail for that. So this is what the what a neural network looks like, and this is the sort of objective that you would use to train it. And now you need to train it. So how do you do that? And again, this is stuff that Tanku talked about. But the first thing that you might do, and I just realized that I went from calling parameters W, which are weights, to theta in the abstract. So these are the same thing. Think of theta as just the set of all the parameters, the weights and the bias parameters and so on. And what we want to do is minimize the error on our training data to learn the parameters. So our training data, there are n samples, and there's an error that we might have on each. So we can get the gradient by summing up the gradients on every individual sample. And once we have that, then what we can do is we can change our parameters against the gradient. We move downhill, and how far we move is proportional to the gradient, and we choose a step size. This is usually denoted by eta, and it's also called a learning rate. As Tankut mentioned, this is very slow because you might have data sets like ImageNet that have 1 million images, and every time you go through, if n is 1 million, then you have to do a lot of work just to make one step of your parameters. So what people have done for a long time is to save compute resources by approximating the gradient on a small batch of data. So this might be order 100 samples instead of 1 million, and then update the parameters again according to that estimate of the gradient that is on that batch, or it's often called a mini batch. So MB stands for mini batch. And so it's useful to keep in mind. So one other ingredient that is very frequently used when training neural networks is to use something called momentum, and that says that the step that you take every time isn't just a learning rate scaled version of the gradient, but actually you inherit, you remember what your what the step was last time, and you keep a lot of that. And this is good for when you have very shallow gradients. And it turns out that doing stochastic gradient descent with momentum works really well for modern neural networks. There are more sophisticated techniques that are good in certain cases, but this will do pretty well for you. This simple idea, and in fact, in many cases, SGD with momentum will actually generalize better than some of the more sophisticated techniques. So I also wanted to give you a little bit of intuition for how gradient descent behaves as you change the step size. There's sort of 4 different regimes that you could imagine being in. One, you have a very small step size, so you get an estimate of the gradient, you take a step, you don't move very far, you take the gradient, you take a small step, and so on. You take these baby steps and you sort of crawl down downhill, and that'll work. But it's a little bit slow. And there's an optimal step size, which if you had a perfectly quadratic error function, you could estimate. And if you did it right, you could in one step jump straight to the bottom and optimize the error. But if you end up being bigger than this optimum, what happens is, rather than jumping to the bottom, you actually jump to the other side of your well. And if you're bigger than the optimum but not too big, you'll jump to the other side and you'll sort of ping back and forth, but you'll fall eventually into the optimum. So things are still okay there. But if you're more than twice that optimum, twice because once will get you halfway across and twice will get you all the way across. If you're more than twice, you'll jump to the other side and then you'll be a little bit higher. And then you do it again, you'll jump to the other side and be higher again. So this time you'll ping back and forth and go out and explode. So this is a bad situation that you would like to avoid. And for a one-dimensional function where you only had one parameter, you can avoid this. But when you have a very high-dimensional parameter space, like a million directions, you really have to worry about the curvature in the sharpest direction causing trouble. So you have to be careful about choosing your step size or your learning rate because of this. So one question about the learning rate is, can we update the learning rate according to the current behavior? Yeah, there are methods that are adapting the learning rate in real time. Learning rate scheduling also is very important. So you don't have to imagine holding this step size or learning rate fixed, but it varies both in sophisticated algorithms in response to what's actually happening, and according to schedules that people determine. So these are the sort of different regimes of behavior that gradient descent has. How do you get the gradient? I'm not going to go through this because with PyTorch and TensorFlow you don't need to, and they have these built-in automatic differentiation frameworks that are really nice. But under the hood, they're essentially implementing something called backpropagation, which if you're not feeling charitable, you could say is just the chain rule. But if you feel that way, I suggest that you take the simplest neural network and don't look at the equations for backpropagation and try to derive them yourself. Essentially what backpropagation does is it tries to solve the credit assignment problem of figuring out, how does the error change when I change every individual unit, every individual parameter in the model. So this was sort of a whirlwind introduction to neural networks. I've omitted, almost everything that is, that has been worked on in the last decade or so. And there are missions that are old, there are missions that are new. So as Tankut mentioned, using a convolutional architecture which builds in translational symmetry and locality into the architecture is quite important if you believe that your data should respect or have those properties. There are a number of more recent innovations, such as something called batch norms, skip connections, thinking carefully about how to initialize the parameters so that learning can take off well, as well as a schedule for the learning rates that I talked about. These are all really important to get deep neural networks with many layers to work well, and they help mitigate something that is called vanishing or exploding gradients. The idea is, if you go back to these equations, to get the gradient, we need these deltas, and these deltas you get sort of recursively by deltas in the later layer. So you start at the end and you go backwards. That's why it's called backpropagation. And every time you multiply it by another derivative, and if you have many layers, you're multiplying many things together, and if those things that you're multiplying together are much larger than one, then you get things that explode. If they're much smaller than one, you get things that vanish. You need to do a lot of work to make sure that doesn't happen, and that you can train very deep networks well. So yeah, I think that probably answered the question that you just asked. You might hear sometimes people say that these neural networks are the same thing that people have been working on for 30 years. What's different? I should have said I put it third, but first of all, there are many innovations from 30 years ago that make these things actually work, that are really important. They seem like engineering details, but they're actually really, really important. But equally important is that we now are in a sort of different regime in some sense, where we have hugely more computational power, largely in the form of GPUs, and we also have a ton more data. So neural networks are able to make use of extra extra compute and extra data in ways that models that were popular 15 years ago, say, are not able to, or have a harder time leveraging these benefits. So we're in sort of like a new world thanks to being in a different sort of scaling regime of these two quantities. Good. So that's the first half. Oh, sorry, it is not the first half. So that's an introduction to some of the basics of neural networks, but they often behave in counterintuitive ways that sort of defy our traditional understanding. And I wanted to tell you about a couple of those briefly. The first is that you might have expected that when you have a big model with lots of parameters, that the error landscape is really rugged. There are lots of local minima you get stuck in. It'd be really hard to optimize. It's very non-convex. And what people have found in the past couple of years is that when you have really big models with lots and lots of parameters that are what you might call over-parameterized, they actually have really simple regions of their loss landscape. That doesn't mean the whole landscape is simple, but regions of it that seem to be the important ones often are simple. I should mention also that when I say loss here, I mean the same thing as error. So people will use loss, error, and risk, you'll see in a minute, sort of often almost interchangeably. So in particular, you could take a neural network on a problem, initialize it randomly, train it up with SGD, and you'll get some setting of the parameters schematically shown here by theta 1. Train up another neural network, same architecture, but re-initialize the parameters randomly, use different SGD like batches when you train it, and you get a parameter here, and if parameter setting here. If you try to interpolate between these two, you would find a region that crosses a big barrier where you get really bad performance. But if you're smarter, you can very frequently find a path from one to the other that goes around like a big valley that doesn't actually cross any barriers. So that's kind of interesting. There's another interesting phenomena that I think, in the interest of time, I'm going to skip, but it's related to the fact that you end up with these valleys where the different models are actually connected to each other, and they're not stuck in local minima. There's this big degenerate space that they can move in. So another sort of interesting phenomena recently is something called double descent, and this calls into question what I told you about when thinking about bias and variance decomposition, and how training performance and test performance change as you change the model complexity. So this is kind of like the diagram that I showed you, that as you collect more data, you fit the training data better, but as you get more complex, you fit the training data better, but your performance will actually reach on test data will reach a minimum intermediate complexity, and then turn around and get worse. What actually happens if you do something crazy, which is to say, you know what, I made my model more complex and it got worse. What if I just keep going? What if I go even more complex? It turns out that in certain cases, that test error goes back down again, and you can actually end up with better performance than the minimum over here. And this is called the modern, if you want, regime, and this is the classical regime. And there are models. So this double descent phenomenon was popularized by Belkin, and this and other papers. There was a recent paper by OpenAI studying this on a suite of deep neural networks, and what they find is that you can actually see this behavior in many of the modern deep architectures. So the best performing models are the biggest ones. And again, this is not the performance on the training set. The training set is you're performing perfectly on the whole time. It's actually performance on the test set. And in some sense, this is surprising, because these are models where you could just set some of the parameters to 0, and then you would get this model. So the fact that when you train with SGD, you get this performance and not the bad performance tells you that it's not just about the sort of expressivity of the model, but actually the optimization, the learning process is really crucial for getting good performance here. And it turns out that also it's easy to see that you can find regimes where, surprisingly, adding more data makes things worse. You might have thought that if you have more data, things should just get better, but actually there are ways in which it makes things worse that you can see from this picture, but I'm thinking I'm going to skip it in the interest of time. Another phenomenon that was really a call to arms for the theory community a couple of years ago did a really interesting experiment where they took a data set and they first took a neural network and a data set, trained it up, and found that if you train on the labels, so airplanes are labeled airplanes and ships are labeled ships and so on, you end up getting 0 error on the training set. And when you ask it about the test set, it performs very well. It generalizes very well. But then what you can do is you can randomize the labels so that sometimes an airplane is labeled a bird, sometimes it's labeled a dog, sometimes an airplane. And then what you find is that the network struggles for a little bit. This is in red, but it's able to actually memorize all of those random labels. And this is really perplexing because this says that that the neural network is a flexible enough model that it's able to learn kind of any labeling of the data that you ask it to learn, but nonetheless, somehow when you give it the true labels, which are the meaningful ones, it's able to generalize. And that's really weird because when you give it random labels, there's nothing to generalize. There's no information because new samples will just be random again. So this has been something that's been very interesting for the theory community. I'm going to skip this. So now what I want to do is in the next 20 minutes or so, maybe I can get through it by then, is tell you about some work that Mingwei, who you heard from recently, has done using sort of physics ideas to understand how the noise that comes from SGD affects the kind of model that you learn in these big deep neural networks. So this is kind of moving to a research level question. So if you have questions about the sort of first half of the lecture, feel free to type them in, and I can answer them, but I'll start moving on in the meantime. So the question that we're trying to think about is there's a surprising thing that happens with SGD, which is that not only is it computationally more efficient, it actually helps you generalize better often. So this is an experiment from a paper from a couple of years ago where people took a network and they trained it either using stochastic gradient descent, using little batches of size like 100, or large batches, meaning like the size of the whole data set. And what you find is that in either case, if you look at the accuracy on the training data, they train out perfectly and get perfect performance. But then when you ask how well they do on the held out data on the test set, you find that the ones that are trained with the stochasticity added with the stochastic gradient descent perform a couple % better than you use the full gradient. And this is kind of surprising because the mini batching was originally designed to be a computational sort of hack to make things faster, but not necessarily to make things better. So now it's amazing. We get something that is more efficient and also works better. So there's a big question of why is that? And the answer that you usually hear is that if you think about the training function, if you imagine it being rugged so that there are many local minima, there might be a minima that's kind of flat, and there might be a minima that's kind of sharp. And who knows, they might have the same training performance, so you couldn't really know which one you should be in, but your optimization will pick one of them. And let's say you end up in the flat one. then when you look at your testing performance is new data. So how do you think about that? Maybe a cartoon to have in your mind is that it's like the loss function on the training data, but kind of like moved around and jiggled. So it's like that's what the dashed red line is. And if you find the flat minima, then that jiggling won't hurt you so much. But if you happen to find the sharp minima, then now your performance, the sharp minima here, sorry, then your performance is actually quite bad. So you would like to find the flatter minima, and the intuition is that the noise helps you find the flatter minima. Check some questions. I'm going to hold off on these questions. So that's the big question for SGD. And there are really two parts to the argument. There's how does the stochasticity in SGD affect the minimum that you find, and how does the minimum that you find affect your performance? And I'm going to focus on the first one. The second question of how do you characterize how well you generalize from the minimum that you find is a hard one. It's sort of different. So I'm going to think about how optimization works. And as I said before, the landscape that we're interested in often doesn't look like this rugged thing. It looks like this big degenerate valley. And so we really want to think about how SGD works in that big degenerate valley. And in particular, we're going to be thinking about the Hessian of the errors. The Hessian is the matrix of mixed second derivatives with respect to the parameters of the error or the loss. And so at a minimum, it sort of tells you the eigenvalues tell you the curvature of the local curvature of the loss in the eigendirections. And what people find is that after training, the Hessian has a sea of approximate zeros that are really like totally flat directions locally, and then just a little bit of stiff directions. And if you zoom in on this this right edge, what you find is that this was a task that had about 10 classes. So it turns out that the model finds approximately 10 stiff directions. There are 10 directions in parameter space that are kind of constrained. And then the sea of zeros. And interestingly, it looks like when you train with the big batches, you get bigger eigenvalues, which means you get stiffer or sharper minima. Whereas when you train with the small batches, you get these smaller eigenvalues. And what we would like to do is actually kind of explain how that happens. And so this is what happens after training. This is at the minimum of the loss, and it turns out that sea of zeros occurs really quite early. So this is an experiment on a big model estimating the eigenvalue spectrum of the Hessian, and at the initialization there are eigenvalues that are big and negative all over the place, but after only 400 steps of gradient descent, they find that there's this huge peak at zero, and it's relatively tight around zero. And there are still some positive directions that have some stiffness. But so this sort of degeneracy locally of the loss landscape happens quite early on. And I mentioned this before, that not only does that happen locally, but there seems to be this more large scale structure of these sort of valleys in which the model is living. And so that motivates the work that Mingwei did, where what he did is he took a network and he trained it with SGD, and every so often what he did is he sent off from like a checkpoint, he sent an auxiliary learning that had a very small learning rate and full batch, so no noise from stochasticity, and looked at where the model landed. And studied the performance of the models at that minimum, and he checked that the models that you find are actually sort of linearly connected. So if you interpolate the parameters, you don't undergo any increase in the loss. And so the standard sort of training curves are in the insets here for two different kinds of models. And what you find is that the training performance gets better as you train more and more. the loss on held out data sort of saturates at some point. But when he looks at the performance of these models on this auxiliary thing that are sort of that are spawned off of the main learning trajectory sort of at the bottom of this valley, he finds that after about 10 epochs, an epoch is a pass all the way through the data. You find that the loss is essentially completely zero on the training set, whereas the loss on the held out data is actually varying as you move along. So the picture that you should have is that the model is sort of bouncing around this big degenerate valley, where at the bottom of the valley, at the floor, there's zero error, but it's still making motion, it's still moving, and at least for part of it, that motion is making you actually perform better, and eventually you actually start performing worse. And we'd like to understand this motion. And I want to emphasize that this is something that happens not necessarily just at the initialization, but only after a couple of epochs of training do you fall into one of these valleys. And so this will motivate for us having a sort of, assuming that the loss function takes a sort of quadratic form where there are some stiff directions. These theta i's are sort of like the parameters that are stiff in the eigenspace of the Hessian, and they have curvatures lambda i's, and there are all these slack directions, these sloppy directions that don't change locally the value of the error, but the curvature, how sharp the curvature is in the stiff directions might be a function of those parameters. So that's the model that we're working with that should happen after a few epochs of training. So let me try and get to what I want to tell you as quickly as I can. So to tell it to you, I need to give you just a bit of notation. So to remind you, we're imagining doing a sort of SGD update of the parameters, where at the next step of learning, we get new parameters that come from the old ones by following the gradient going against the gradient on the mini batch. And we need to think about what happens on average. We don't want to make statements that depend on a specific mini batch. So we want to average over realizations of the mini batch. And so that notation sub MB is imagining averaging over the mini batch. So for example, the gradient averaged over a mini batch is just the actual gradient. And then one concept that we need to think about is an average in a stationary distribution. So if SGD is kind of like found a nice minimum and sort of bouncing you around and kind of equilibrated the system, you could ask about averages of quantities in that distribution. So the bracket averages are averages in that distribution. And in particular, we're going to focus on averages where you've averaged where you've equilibrated or you've become stationary only in those stiff directions. And they're still slack directions, so you probably aren't going to equilibrate in them because you just spread out. But you've sort of equilibrated in the stiff directions, and then there will be sort of motion in the slack directions. One other quantity that's important is the covariance matrix of the noise. And that's, you take the derivative with respect to some parameter I times the derivative with respect to some parameter J on a mini batch, and you average that with respect to mini batches. So if those are correlated, that will be a positive component in this matrix. And in physics, you would often make this a connected correlation. You would subtract the mean, but it turns out that this is the more natural quantity to have here. So let me quickly tell you what we can say. So what Mingwei was able to prove is that when you're in this minimal valley, if you have a sort of timescale separation where you've reached stationarity in the stiff directions, then there's a sort of entropic force that pushes you in the degenerate directions in a way that reduces the trace of the Hessian, that is the sum of the eigenvalues or the sum of the curvatures. So people talk about how SGD finds flatter minima, and we had this cartoon a couple slides back, and this is what we think is the right way of saying how SGD finds flatter minima. It finds minima that reduce the trace of the Hessian. And to illustrate what I mean by having a stationary state or a timescale separation, here's a toy example where you have 4 parameters. You have 2 with stiffnesses, and then the stiffnesses of those 2 are parameterized by these slack directions that don't have curvature themselves. And if you do sort of a toy version of SGD on this, what you find is that in the directions 1 and 2, you quickly equilibrate and you sort of just bounce around in these 1 and 2 directions, and then you get slow motion in the 3 and 4 directions that presumably decrease the sum of these 2 quantities. Great. So that's our theoretical result. To show you that it works, Mingwei took that experiment from a couple slides back with those projected paths and looked at the trace of the Hessian, or estimated the trace of the Hessian, and overlaid here in blue is that validation loss, the held out loss from before. And what you see is that the trace of the Hessian is indeed monotonically decreasing with some noise. But actually the validation loss reaches a minimum here somewhere around 40 epochs in this architecture and 50 in this one. And so while the trace of the Hessian makes things flatter in some sense, and maybe has a correlation with generalizing better, it's not perfect. And in fact, even though you decrease the trace of the Hessian, you actually start performing worse. So this leaves open the possibility that you could find ways to change the noise and generalize better. So that actually motivates. Let me skip to there. What I think is a really exciting thing that Mingwei realized, which is that if you don't just live with what SGD is doing, but you actually add your own noise. So imagine you did regular gradient descent, but you added your own noise. If you had some function of the Hessian spectrum that was monotone in this sense, so X here would be the eigenvalues of the Hessian. What you can do is you can add your own noise that has a certain kind of structure, and then you can make that quantity F that you were interested in decrease. So for example, if F were the log product of the eigenvalues, then it turns out that the noise that you would add should be isotropic, and that actually makes the determinant of the Hessian decrease, which is potentially an interesting quantity. So this is pretty cool. And just to show that happens, Mingwei took a toy model where the trace of the Hessian and the determinant of the Hessian were designed to be anti-correlated. And then he added either isotropic or SGD-like noise. And what he found is that when you add SGD noise, as expected, the trace goes down, but actually the determinant goes up. But when you add isotropic noise, then the trace goes up and the determinant goes down. So this is really promising for allowing one to design noise structures that help you find models that have local curvatures that are useful for whatever you would like, whatever you think useful means. So that was sort of a whirlwind summary of that work. I think I've approximately finished on time, so we have a couple minutes for questions, both on that latter bit and also on the first half. Let me take a look and see if I can say anything about the ones that have been asked so far. So there's some questions on the first part. One question was, how does nonlinearity help? Well, so if you didn't have a nonlinearity in a neural network, then you just be composing linear functions. So there would be no real point in some sense in having depth for expressivity. You could write the model as just a single linear transformation. There's some subtlety there, and having depth even in a linear model does change the way optimization works. So there are interesting papers on deep linear networks that study that. But if you want to have a model that is more expressive, then you need to add nonlinearities at each stage. So there was a question about the benefit of larger models in connection with the lottery ticket hypothesis and pruning networks. It's a really interesting question, and in some sense, the lottery ticket hypothesis got a lot of attention because it appealed both to practitioners, because if you have a smaller network, it's faster to train, it's smaller to put on a device and run inference. But also it gets to deep theoretical questions about overparameterization and optimization and so on. And I don't think I can answer them in full generality. There was, I think we sent you all a blog post that connected to some of those questions. That's worth looking at. There was a question about why look at the Hessian. So it's a reasonable question, and if you think that the local structure of the loss landscape is interesting, it's sort of a natural quantity to use. There are other local quantities like the Fisher information or the noise covariance matrix, also called the empirical Fisher. These all seem to look very similar once you've trained. But the intuition, for at least from older works, is that the local curvature should tell you something about the flatness of the model, and maybe that can speak to something about generalization. Although it's not reparameterization invariant, for example, you did perform your gradient descent in a certain parameterization, so it is maybe meaningful to look at it. With regarding to adding our own noise, then I think the idea would be that we're adding our noise in a certain way because we think we understand what that will do. So rather than opening up the model and trying to figure out what noise did, we'd be adding noise specifically because we think we know what it does. See, any more questions? Maybe I will share. Okay, great. So if there are no more questions, thanks so much for listening, and I hope you all had a great time at the summer school. Oh, I'll let Svetlana or Halima address that. Great. So thank you all very much. It's been a pleasure.